Hello, welcome, and thank you for watching this video about simplifying radical expressions. So we've got several objectives over here. Use the product rule for radicals, use the quotient rule for radicals, simplify products and quotients of radicals with different indexes. We'll use the Pythagorean theorem and use the distance formula. We'll start with our product rule for radicals. So as long as the nth root of a and the nth root of b are real numbers and n is a natural number, then if you have the nth root of a being multiplied by the nth root of b, so you're finding that product, you can write that as the nth root of a times b. Likewise, if you have the nth root of a product, you can split that up as the nth root of a times the nth root of b. So again, it works both directions. We'll use that kind of going both ways as well. So looking at using that product rule, we're going to be multiplying together here. So for the first one, the square root of 5 times the square root of 7, we could write as the square root of 5 times 7. Of course, you might also just jump right to the square root of 35. The second example, square root of 2 times the square root of 19. Again, you could multiply the square root, or you could do the square root of 2 times 19, which of course would be the square root of 38. And with all of these, if you could simplify them, you would. And we'll get into a bit more simplifying later, but these really don't simplify. For example C, square root of 11p, and example D, we would do 7 times 11, so 77, and then x, y, z. So really just multiplying those together like that, and that's our product rule. Again, take a look at these ones. Now notice they're different indexes. Now we've got cube roots, fourth roots, sixth roots, but the key being that they're the same. And we are assuming that all variables represent positive real numbers, so we're not going to have to worry about doing absolute values at all. That's what that really means. So for example A, we can do the cube root of 3 times 12, which of course would be the cube root of 36. And again, we can't simplify that at all. For example B, we have the fourth root, and 8 times 3 would be 24, and then r squared and y. Again, can't really do anything with those, so it's just r squared times y. Example C, we would multiply the 10 and the 5 together, we'd get 50, and when you multiply m to the fourth by m, we just follow our normal exponent properties and add those exponents, we get m to the fifth power. And then when we have something like a fourth root of 2 and a fifth root of 2, we can't use the product rule as a way to simplify that. We will take a look at an example where we can get a common index, but for now we're just saying we can't use the product rule to get that done. Now the quotient rule is very similar to the product rule. If you have a radical of a quotient, like we have here, the nth root of a over b, you can split that up as the nth root of a over the nth root of b. And likewise, you can do that in reverse. If you have nth root of a over nth root of b, you can put that together as the nth root of a over b. For the first example, the square root of 16 over 25, what we want to focus on is splitting that up. 16, square root of 16 over the square root of 25, and we look at it that way because both of those can be square rooted, so we get 4/5. For example B, we would have the square root of 7 over the square root of 36. Now the square root of 7 we can't do anything with, but the square root of 36 is 6. Example C, we can do, and with this negative here, you can actually pull a negative out of a cube root, or if you want to, you could think of that as being with the numerator or with the denominator. Either way, it'll work out just fine. Again, we can cube root negative 8, we get negative 2, and we can cube root 125, we get 5, so negative 2/5 for that. Now if we look at the cube root of 7 over 16, we can't do anything with the cube root of 7, but we can cube root the 216. That will give us 6. So we get the cube root of 7 over 6. And we get a variable here, so we'd have the fifth root of x over the fifth root of 32, and the fifth root of 32 is 2. so 5th root of x over 2. And then for f, notice we've got the negative on the outside, and so it's a little similar to c, and really negatives can move freely in and out of odd roots. It's not the same for even roots, but it does work that way for odd. Here we would again have that negative, and then the cube root of m to the 6th, and the cube root of 125. Now again, when we're cube rooting in m to the 6th, we're saying, what can we multiply by itself 3 times to get m to the 6th? So we just divide the 6 by 3, we get m squared. And then the cube root of 125 is 5. So negative, and then m squared over 5. And again, that negative can be out front like I've got it. You could put it on the m, so I can negative m squared, or you could have m squared over negative 5. All those would be acceptable. Now so far we've had either radicals that simplified completely or simplified not at all. So there is in between. Conditions for having a simplified radical. The radicand has to have no factor raised to a power greater than or equal to the index. If it does, it can be simplified. The radicand has no fractions, so you can't have a fraction inside or part of a radicand. No denominator contains a radical. And exponents in the radicand and the index of the radical have no common factor except 1. So again, there's a few rules there. We'll take a look at what that turns into when we're looking at these questions here. So the square root of 24. Actually, what I'm going to do is I'm going to use my product rule to split that up, and I split it up in terms of factors of 24, but specifically I look for factors that would be perfect squares, so I'd use 4, and then 6 is really just kind of left over. There's no perfect square factors for 6 other than 1, and so we end up with 2 square roots of 6. Likewise with the square root of 108, I try to split that up using 2 perfect squares, or sorry, a perfect square, and then whatever I have to multiply that by to get the 108. So here we'd be looking at 36 and 3, and so that would be 6 square roots of 3. Now looking at something like a square root of 10, square root of 10 is actually simplified already. The only perfect square factor that it has is 1, which does not help us reduce it. If you look at the other factors for 10, 2, 5, and 10, none of those are perfect squares. So square root of 10 is all we can do there. That's it. Now looking at example D, we've got the cube root of 16. So now it's a little different because we're thinking of, okay, what perfect cube factors are there for 16? Well, 16 is 8 times 2, and 8 is a perfect cube. So we can cube root the 8, we get 2, and then the cube roots of 2 have to just stay there. That's it. So 2 cube roots of 2 for that one. And then the last one here, the negative 4th root of 162. And again, you can use your calculator to help you figure out perfect fourths if you like. So we'd be looking at the negative sign, and then what perfect fourth would go into 162. So in this case we would use 81. 81 is 3 to the 4th. 81 times 2 would be 162. So we take the 4th root of 81, which is 3, and so we end up with negative, and then 3, and then the 4th root of 2. So that's what we'd be looking at for example E. And now we have some variables included. So same sort of idea. We would set up 2 radicals, one for the stuff that will perfectly fit, like 16, and m squared, and the other for the leftover factors that can't be square rooted. So in this case we'd have 4m times the square root of m. And for example B, we're still talking square roots. So again, we'd be looking at how to split that up. So the largest perfect square that goes into 200 is 100. And for the k's, we just take the largest even exponent that we have. Again, all even numbers are divisible by 2. So we take k to the 6th, and then we need a q to the 8th. So all of the q's. And what we have for leftover is just a 2 from the 200 and 1k from the k to the 7th. And so we square root this first radical, so we get 10k to the 3rd, q to the 4th, and then the square root of 2k. And again, remember, we are assuming that all the variables represent positive real numbers, so we don't have to worry about absolute values at all. Example C. So again, we split this up into cube roots, and we'd be looking at taking the entire negative 8, an x cubed, and a y cubed. So again, these are the, again, negative 8 is a perfect cube. With the variables, what we want is the exponent to be a multiple of 3. So 3 is the biggest multiple of 3 that's less than 4, and it's also the biggest multiple of 3 that's less than 5. So we take what we can out of that. So we didn't have any numbers left over, but we would have a leftover x and a leftover y squared. Notice in here that our exponents are all less than 3. If you have an exponent here that's 3 or greater, that means you should have put more over here, and you want to take care of that. So we just cube root what we can. So this first radical, we can cube root this, so negative 2xy, and the cube root of xy squared. So that's what we're looking at there. Now the last one here, we've got example D, we've got the negative out front. We'd have a fourth root that we can do, and then a fourth root that doesn't work. The fourth root that goes into 32, well, 2 to the fourth is 16, so that leaves us with a leftover 2 here. And then the biggest multiple of 4 that's 9 or less would be 8. That leaves us with 1 there. So we fourth root the 16y to the 8th. The negative would come down as well. So fourth root of 16 is 2. And again, really we're dividing the 8 by 4. We get y squared. And then the fourth root of 2y. And so that's how that one simplifies. Alright, so here we're looking at simplifying radicals. They don't simplify in kind of the more traditional sense. What I find to be the easiest here is to think of these in terms of rational exponents. So the 9th root of 5 to the 6th power would be 5 to the 6/9 power. Now that fraction I can see pretty clearly reduces with a common factor of 3, so it would end up being 5 to the 2/3 power. Which then, if I switch back to radical form, would be the cube root of 5 squared. So that's a bit simpler and simplified really compared to the 9th root of 5 to the 6th. The fourth root of p squared would be a similar problem. Switch it to rational exponents, we get p to the 2/4, and then we can see that that's really the same as p to the 1/2, and so that would really just be a square root of p. So square root of p being a bit simpler than the fourth root of p squared. So again, they might say simplify using smaller indexes. To me, it makes sense to simplify that by using rational exponents. Along those same lines, we have how to multiply radicals that have different indexes. So if we have a square root of 7 times a cube root of 2, our normal radical properties don't apply because our normal radical properties require a common index. And even if we switch them to rational exponent form, we'd be multiplying 7s by 2s, so we can't use our rational exponent properties. So we actually kind of combine the two. And so what we look at doing is, because the indexes are 2 and 3, it's almost like having a common denominator. Their least common index would be 6. So we use rational exponents to write each radical as a 6th root. So here's the way that process would go. We're starting with a square root of 7, which is the same as 7 to the 1/2 power, which if we convert to 6th root would be 7 to the 3/6. And so that's the 6th root of 7 to the 3rd power, which ends up being the 6th root of 343 when we figure out 7 to the 3rd power. So we converted that so it would be a 6th root. Now that's not simplified, but again, our goal isn't to simplify that, it's to get it so that we can put these together. We do the same sort of process for the cube root of 2. That's the same as a 2 to the 1/3, which if we convert that to a 6th instead, would be 2/6. So that's the 6th root of 2 squared, which would be the 6th root of 4. So now these are both 6th roots. So again, we started with a square root of 7. That's the same as the 6th root of 343. We started with a cube root of 2. That's the same as the 6th root of 4. Now these have the same index. We can use our regular radical properties, and kind of the one thing that they skipped in here was showing that it's 343 times 4, and then that's how we get the sixth root of 1372. And that's simplified as much as possible then with that sixth root of 1372. It's all together as one radical, which is what we want. One place where we have to deal with radicals is when we're using the Pythagorean theorem. So hopefully you remember this. The Pythagorean theorem relates the lengths of the three sides of a right triangle. So C being the hypotenuse, and A and B being the two legs, a squared plus b squared equals c squared. Now here, this equation is solved for c squared. You, of course, could solve it for a or b as well, but this is kind of the typical way that we write that, a squared plus b squared equals c squared. So we'll use that here in order to find the length of the hypotenuse. And when we do that, we'll try to reduce that down as much as possible. So in this case, we have the two legs. So 6 squared plus 4 squared would equal c squared. 6 squared is 36, 4 squared is 16. So we would add those together, we get 52 equals c squared. And so we square root both sides. Now, because of the context of this question, when we square root both sides, we don't have to include the positive and negative because c is a non-directional distance, so it cannot be negative. So we would have c equals that square root of 52, and then we would look to see if we could reduce that at all. And there is a perfect square that goes into 52. 4 goes into 52 13 times. Square root of 4 is 2, so the length of the hypotenuse would be 2 times the square root of 13 when we reduce that down. Now, related to the Pythagorean theorem is the distance formula. So if you have 2 points on the coordinate plane, x sub 1, y sub 1 being one point, and x sub 2, y sub 2 being the other point, then the distance between them is the square root of x sub 2 minus x sub 1 squared plus y sub 2 minus y sub 1 squared. Now, once you've done this for a while, you realize that the distance formula is really just solving the Pythagorean theorem for c specifically. So you can, feel free to go ahead and plug your points into this formula if you like. Personally, I prefer just to kind of make a little sketch and use the Pythagorean theorem in order to figure out what's going on for the distance. So they give me the points negative 3, 5, and 6, 4. Now I don't feel the need to do a fancy sketch for this, but negative 3, 5 would be somewhere around here, and 6, 4 would be somewhere around here. So we got negative 3, 5, 6, 4, and what I do is I just make a right triangle between those 2 points. And I just need then to find out my distances for my vertical and horizontal sides. Well, the vertical side goes from 4, because this would be at 4, up to 5, so that's a distance of only 1. The horizontal side goes from negative 3 to 6, so that would be a distance of 9. And so, without too much work, I can figure out what my triangle would look like, and of course that's a right angle because it's a vertical and a horizontal side. And I can set up my Pythagorean theorem. Now, if you'd rather plug it into the distance formula, again, feel free to do that. This is how I would go about this. So I could set that up, 1 squared plus 9 squared equals c squared. And again, notice, our x sub 2 minus x sub 1 squared. Well, again, that's really just my 9 squared. We did the 6 minus the negative 3, that gave us 9. And the y sub 2 minus the y sub 1 squared, well, that's just the 5 minus the 4, that gave us 1, so we do the 1 squared. And so when we do this, we end up with, of course, 1 and 81 equaling c squared, and so we get 82 equals c squared. And so c would equal the square root of 82. And the square root of 82 does not reduce, so we just leave that alone. So we get that for our answer. Thanks for watching. Hopefully this was helpful. Again, you'll want to take a look at some example problems and try those on your own. If you have any questions, again, feel free to let me know.